continuing between 0 and 8. Oh, wait, that's not supposed to be closed and then that we can stay close.
Does it mean closed?
Because this isn't a closed curve. Let's take a look at this actually. So we'll go and plot this path. That's the entire curve. Which is pretty interesting looking curve. That's not what we're interested in. We're interested in going from 0, 0 to 2, 1. Just that. There's the curve of interest. And we add, no, not do add. Really annoying.
Is it going
No, not going at all. So we're following that path. From there. Notice this is not a closed path. Since it's not closed, we can't use Green's theorem. Green's theorem is only for closed paths. However, if we're lucky enough for this vector field to be conservative, we can still use the fundamental theorem of line integrals. There's the vector field. The cross partials are equal. F is therefore conservative, which means this integral is path independent. Now, what we could do is try and find the potential function, right? That would work. But there's another way of doing it. Path independence means it doesn't matter what path you take, as long as you go from the starting point to the ending point.
So why doesn't it
So
matter?
just use that one
Why doesn't it matter?
because it's conservative.
But wouldn't it be conservative along the original?
Right. But because it's conservative, the path you use doesn't matter. All that matters is where you start and where you end, not how you get there.
So if it's conservative, any route to those two points is.
You can use any path you want. Why don't just use that straight line path? This is, I think, easier than doing the potential function. Isn't that line just the line y equals 2x? Oh, I'm sorry, not 2x. Half x. So go 2t. Then t would go 0 to 1 because x goes from 0 to 2. So integral 0 to 1. That's 2 to the 4th. 16 times 10 is 160. That's going to be 4t to the 4th. And dx is 2 dt. And then it's just a matter of 3x squared, y squared, 2 squared is 4, 12, t to the 4th. dy is 1 dt. You can factor out a dt. 160 minus 4 is 156. 156 times 2 is 312. 312 minus 12 is 300. There's the inverted finding. 300 divided by 5. Uh-oh. It's 60. That's 60 t to the 5th from 0 to 1. The integrals are 60. And so don't fall into the trap of always trying to use Green's theorem. Green's theorem only works on closed paths. You have to enclose a region. Show area bounded by a simple closed curve C given by half integral C of x dy minus y dx. And so we have a curve C that's enclosing a region D. We can use Green's theorem. This will give us double integral over that region. Partial x of x minus partial y of negative y dA. Isn't that just 2 times that double integral? But what's that double integral? If you just integrate over a region of the area differential, what do you get? Isn't it just area of the region? Solve for area. Area is a half dimensional. We're going to use that now to find the area of an ellipse. Center of the ellipse is the origin. And it has semi-major, semi-minor of A and B. We don't know which is the semi-major, because that would just be the larger one. For an ellipse, what are the limits of integration on theta? Oops, I forgot my one hand. What are our limits of integration? Theta goes what to what for an ellipse?
Zero.
Zero. What is it? It's still too high. And if you think of an ellipse, as you rotate your radius, it's still going to go 0 to 2 pi, right? It's just as you rotate, the length of your radius is changing. But the line itself is still that, the radius still forms an angle from 0 to 2 pi as you go all the way around. X is A cosine theta times dy which is B cosine theta d theta minus y is B sine theta times dx negative A sine theta d theta. The integrand, aren't you just left with AB? So I can factor out, you're left with AB over 2, integral 0 to pi of d theta. What's that integral? What's the integral 0 to pi of d theta? It's just 2 pi. You're left with pi AB as your area. That's probably the easiest way of finding the area of an ellipse. So you want to evaluate this integral along the given curve. Is that curve closed? Yeah, that's right. And that's the region it's enclosing. We can use Green's theorem. Describe that region.
Zero is less than, x, which is less than y is 0 is less than y, which is less than 1.
Not one. They'll give you that rectangle. One hand again and give you a rectangle. Give you that rectangle. Hmm? No, definitely not y equals x. So the degree is going to go to that line, right? What's the equation of that line? Sine of x is in the line. Find the equation of the line.
Are you
Well, that's slope-intercept form, which is the most standard form of the line.
Rise over run.
What's rise over run?
The line. Slope.
Slope.
Yeah.
What's the slope of this line?
It's 1 over 2.
Which is what?
2 over
What does B represent?
5. The 1 or the
The front,
Which is what?
or which is
1 and 0.
not.
There's your equation. No, there's something that does cross the y-axis. Every line has to cross the y-axis. It just crosses it at 0. There's your region. We want partial x minus partial y dA. There actually was something else I should have checked. Is that curve oriented counterclockwise? Yes. If it's not, you can't use Green's theorem. There's the integral we want to evaluate. Oh, well, that first integral is easy. Yeah. That integral values. Let's back out at -2 over pi. Left with x minus x sine of x. Well, that first one's easy, isn't it? Just x squared over 2. X squared over pi from 0 to pi over 2. What about that x sine of x? How'd you do that?
Product of
That's a discriminative.
the,
What's the product of integration?
it's
It's not really a quote unquote product. Well, yeah, it is. It is product rule. Sort of. Yeah, it's integration by parts. When you do it, you're going to get sine x minus x cosine x. It's also an integration tool. Or you could just use your calculator.
Would you want us to like write down in our steps? Like use
No, because you could just go from that very first line I wrote and evaluate that double interval, that intermediate. You don't have to do any of the intermediate steps. Unless I specify that you're not allowed to use a calculator. Pi over 2 squared. Pi squared over 4. Divided by pi is just pi over 4, right? What's sine of pi over 2? What's sine of 0? What's cosine of pi over 2? Times pi over 2.
Wait, times cosine of pi.
Cosine of pi over 2? You said 0 times pi over 2.
0.
0. What's cosine of 0?
1.
Times 0. That's just 1 minus 0 minus 0 plus 0, which is 1. There is your interval. Pi over 4 minus 2 over pi. For funsies, evaluate that line interval directly. So you can't use Green's theorem. And verify, you get pi over 4 minus 2 over pi. Question on Green's theorem.
Good.
Easy, Green.
Who's for you to say?
I wish I could do this all day. For this one over the next one, we're going to look at. So let's get into the group. And let's just say, like 40, no, 30. 38 minutes. And yeah, go to 45. There's only 2 more worksheets after this. That's a shame. I'm almost done.
He's like pulling away as I'm getting there, and I'm like, no!
You see
I'm like, no, I know you see me. I know you're doing this just to be evil. It's always the ones at night too. All the night shift bus drivers are the worst.
Yeah.
The guy in the morning is this like super nice old man who like waits at like you stop for like 10 minutes, and I'm like, all right, I know I have some time to get to the stop in the morning.
Here's Stokes' theorem. Stokes' theorem sucks.
That's what you're starting off with?
Well, I'm doing both. Takes circulation and turns it into flux. And specifically flux of the curl, which is awful. Right, so this requires matching orientation. Right, so you have orientation of the curve, which has to be counterclockwise, and positive orientation. So if you have to imagine yourself walking around the boundary of the curve, of the surface. Hold your right arm out. The direction, so if you're walking in the positive direction, the direction of the orientation of the curve, your arm points in the direction of the normal vectors to the surface.
Is this like right?
Not really right-hand rule. Right-hand rule deals with cross products, but it's very similar. Right, so in this case, you just imagine you're on this circle and you're walking with your right arm held out. It's pointing outwards from the surface. So you have outward pointing normal vectors. That's how the surface will be oriented. So important to note, not that it matters here if you're going in this normal direction from circulation to flux. Your surface is open. Open surfaces have a boundary. Closed surfaces do not have a boundary. So if you're trying, because you can also go in the opposite direction. Or if you want flux of a curl field, you can write it as the circulation along the boundary. But if that surface is closed, then you can't use Stokes in that direction because you have no boundary. That is where divergence theorem comes in. Divergence theorems let you take flux as a triple integral of divergence. Again, it's important to note divergence theorem only applies if your surface is closed. If it is not a closed surface, you cannot use divergence theorem. One of the questions I had on my other Calc 3 quiz, it was an online course, had to do with finding the flux of a force field through the portion of the surface of the sphere located in the first octant. And everyone used divergence theorem. It's not a closed surface. This whole sphere itself is closed, but you just look at a portion of it that's in the first octant that's not closed.
So is there a way you can do it where you're going through the whole sphere and then you just divide your answer by 4?
No, that does not work. Because you have to remember, what you're assuming is that the flow is equal through all portions of the sphere. Depending on the field, it may not be. What you could do is treat it as a closed surface, where you have the planes are bounding it. So all you have to do is evaluate the flux through each of those planes and subtract it from divergence theorem. But why you would do that? Because that's going to require a lot more work. But you theoretically could. So if it's, let's say you only need one more surface to make it closed, it might be easier to use divergence theorem, calculate the flux just through that portion that will close it, and then subtract. Right, 'cause you're losing that flux. So I think I'll spend the rest of class today just doing the Stokes theorem problems. No, I don't want to use all of the 50. So I'm only going to have 20 next time. So let's say we'll do about half an hour today on Stokes, then half hour on divergence, and then the half hour on your worksheet on Wednesday. And then after that, we'll go to the review worksheet. So this is it. We're almost done. Verify Stokes' theorem. What does that mean? That means we have to do both circulation and flux and show that they're the same. So we're dealing with the boundary of the upper hemisphere, x squared plus y squared plus z squared equals 1. So we'll start with the circulation. All right, this symbol, the del S, is boundary of S. Right, so the partial S, we just mean boundary of. In Green City, you may have seen something similar. Represent your curve as boundary of D. We need to parameterize our curve. So we're dealing with upper hemisphere. So what does the boundary of the upper hemisphere, what kind of curve is that? What kind of curve is that? Remember the boundary. This is the boundary of it's a circle. Specifically, it's the unit circle. Because this is the upper hemisphere of the unit sphere. Since it's the upper hemisphere, it's on the xy plane, z is 0. And it's the whole circle, 0 to 2 pi. And of course, we're assuming positive orientation. Two x minus y, negative yz squared, and negative y squared z, that needs to be evaluated along the curve. Oh, but z is 0. There's your integrand evaluated. Dotted with r prime. D theta. So again, since these two components are 0 and you take the dot product, we just add 0 to the entire dot product. So we just need this. First component times negative sine of theta. So we can use double angle identity on sine. Oh. That would integrate out to 0. Now use reduction identity on sine. And that goes out to 0. You're left with pi. So we'll call that value number 1. Now for the flux. Two things we need. First, we need curl. You know how to find curl? Partial y negative 2yz minus partial z negative 2yz. Partial z minus partial x. Oh look, that's also 0. Partial x minus partial y, you get negative 1. The curl is 0, 0, 1. We now need to parameterize. Since we're dealing with the hemisphere here, it was upper hemisphere, right? Theta goes 0 to 2 pi. Phi goes 0 to pi over 2. Normal vector. It's just sine phi times parameterization of a unit sphere. You just have to make sure that that's pointing in the right direction. That is, in fact, outward pointing, which is the direction we want. So we'll do this. double integral over the domain. Zero, zero, one evaluated along the surface is still 0, 0, 1. Dotted with sine phi. I'm going to need more data. Let's move this. Dotted with the normal vector. Oh, look at that though. Isn't this just going to be sine phi cosine phi? D phi d theta? Let me actually take that dot product. And there's no theta. I'm actually going to do this. And so integrate with respect to theta, you're going to get 2 pi. I'm also going to use the double angle on sine, right? Sine phi, cosine phi is a half sine of 2 phi. We're left with pi integral 0 to pi over 2, sine of 2 phi d phi, right? What is cosine of pi? What is cosine of 0? What's negative 1 minus 1 times negative pi over 2?
Negative 2 times.
Negative pi over 2 times negative 2. We'll call that number 2. Are 1 and 2 the same? Where we calculate for the circulation? Stokes theorem has been verified. Now we just need to evaluate some circulations using Stokes theorem. The curve, x squared plus y squared was 9, located in the xy plane, oriented counterclockwise when viewed from above. So the idea is, what surface does x squared plus y squared equal 9 act as the boundary of? We just did it. It's a hemisphere. In this case, the hemispheres of the sphere of radius 3. Because our boundary is radius 3. There's our parameterization, there's our normal vector. Since it's counterclockwise orientation, we need to have outward pointing normal vector, which that one is. We also need the curl of F. You get 0, 0, 1. Using Stokes' theorem. Circulation in question is this flux integral. Right? So double integral over our domain. We said the curl was 0, 0, 1. Dotted with our normal vector. dA. Again, that is just going to give us 9 sine phi cosine phi dA. But then we just evaluate that. Right there. That double integral is just 1. Oh, I'm sorry, not 1. It's pi. Right? From the previous problem. 9 times pi, just pi, and we're done. Circulation over the boundary of the triangle cut from x plus y plus z equals 1 by the first octave, oriented counterclockwise when viewed from above. Oh. I used the wrong file. Oops. Wrong damn file, so give me a minute. Uh,
Are we working with this one ourselves?
No, I used the wrong account, so I'm trying to get the file so I have the right account. Of course, I should install the latest one on this device, so I'm doing that as well. Okay, so apologies, this is what we want. Let's go ahead and download this. Thank you very much. Now, sign back in. Let's go ahead and count this time. Oh, it doesn't want me to upload. You've got to be kidding. That is freaking annoying. Whatever. Here we go. And so that's the plane x plus y plus z equals 1 cut off by the first octave. Got two, I think. right, and then viewpoint above, just to see. So here's our surface looking down. It's oriented counterclockwise from this viewpoint. Right? So from this viewpoint, we're going this way, right? So we're going to have an outward pointing normal vector. Now let's get a view that's a little bit more useful. That's a bit more useful.
Do you use Wolfram for like all of your classes?
Well, except for pre-calc, like classes that
Yeah.
don't really need it, but everything above pre-calc, yeah.
Gotcha.
There's our surface. It's that yellow triangle. No, you can't see the screen yet, but that's fine. So I'm going to keep this anyway. I'm going to go back to above. On here. And then I'll switch back to it because I will need it. Yes, yes, it's okay. Later. So for now, back here. We need to parameterize this surface. Well, the surface is easy to parameterize. Isn't this z equals f of xy? Z is 1 minus x minus y, right? That makes the parameterization really simple. Now we need a domain, which is where I'm going to come back. Here. So you have to imagine that this is the xy plane, right? X, y. This line, right? So our domain is that triangle on the xy plane. X would go 0, 1, right? Y would go 0 to this line, which is y equals x, isn't it? I'm sorry, not y equals x. It's y equals 1 minus x. Right, because it's if we come back, I can leave it there. If you set z equal to 0, you get x plus y equals 1. So y was 1 minus x. The only other thing we need now is curl. And I do not feel like doing this by hand.
Oh, I'm sorry, I'm also gonna need the normal vector.
What, y squared plus z squared, x squared plus z squared, x squared plus y squared. Huh? I don't know how to use curl. No, apparently not, okay. That's what I need. There's the girl. Notice you can factor out a 2, right? Y minus z, z minus x, and then x minus y. Normal vector, negative partial x of z, negative partial y of z, 1. There's your outward pointing normal vector. So we need to evaluate f, or sorry, the curl along G. Y and x stay the same. Z becomes 1 minus x minus y. I'll let you do the algebra. Dotted with 1, 1, 1 dA. I'm out of time for Stokes, so I'll let you do the evaluation. You'll get 0. Just verify it. That dot product winds up giving you 0. So you should get this. Verify the divergence theorem. The region in question is not a cylinder, or the surface in question is a cylinder.
Yeah.
And so what you have to imagine is plane z equals 3 cuts there. Plane z equals 0 cuts there. And then this is given by x squared plus y squared equals 4. How many surfaces are there? on that closed surface, because that is a closed surface. So how many surfaces is that?
How many surfaces is looking at?
Does that surface have here? Does that entire surface have?
Three.
3, top, bottom, and then the lateral part, right? So in evaluating the flux integral, we need 3 parameterizations. The top, so let's just look at that. Top is a circle on the plane z equals 3, right? So obviously it's going to be something, something, 3. But it's a circle. What's the radius of our circle?
Oh, 2.
It's 2.
Yeah.
Oh, except, forgot, that's going to have to be RR. Right, because it's the surface, so it's that entire circle, so you have a changing radius. We need outward pointing. So it's going to be going up in the positive z direction, right? With a magnitude of r. So 0, 0, r. Now for the bottom. Same thing, except z is now 0, right? But n this time has to be pointing downwards. 0, 0, negative r. Now for the lateral.
What's the single substrate?
L. Well, that lateral, remember, we're only working with the surface, has radius 2, right? So it's going to be a circle of radius 2 that extends along the z-axis. Now we need the normal vector. Well, it's not going to be pointing anywhere in the z direction. And since we're going around, it's going to be 2 cosine theta, 2 sine theta. And now just make sure that's pointing in the right direction. Is that always pointing outwards? Yes. It's always pointing away from your surface. Double integral d top. F evaluated along G. Dotted with 0, 0 RDA. Plus double integral along the domain at the bottom. Oh, that one was easy. Plus now your lateral part. You should easily see that middle one goes to 0. That dot product is 0. Do the dot products. This is what you get. So I want you to go ahead and evaluate that at home. And on Wednesday, tell me what you get when you do that, when you do those intervals. Last homework is due next Monday. Last homework covers Green's theorem, Stokes theorem, and divergence theorem. And continue to work on that reference sheet.
So for this case, just the working relationship.
Yeah, one more homework. But Wednesday we'll pick up with divergence theorem. So we'll finish that verification. A couple more problems on divergence theorem, and then it's just worksheets for the rest of the class.
I sent you an email about this guy. What's it called? I was doing a quiz, and in the middle of it,
I responded before class. I reopened it. Oh, tomorrow, so trying to get something.
I will. I did regularly send the email. That thing happened. Yeah.
So you want this?